Alright, so welcome to page 2. This is still dealing with the question from before, so we're still going to use this given Maclaurin series. So the Maclaurin series for g evaluated at x equals 1 half is an alternating series. So basically what they're saying, if you plug in 1 half right here, so again, just like if we plugged in -1 or 1, if we were to plug in any number in this interval, we're going to get a different type of a series. So we're going to get some kind of a series. So if I plug in 1 half, I'm going to get a series. Um, yeah. So in any case, they're plugging in 1 half, and they're telling us that it's going to be an alternating series whose terms decrease in absolute value to 0. Basically saying here that it's converging by the alternating series test. The approximation for g of 1 half using the first two terms of this series is 7 over 120. So what they're saying there is, now we're going to focus on the polynomial part. By plugging in 1 half here, 1 half, 1 half, 1 half, by plugging in 1 half for x right here and using the first two terms of the Maclaurin series, the polynomial, this right here will be equal to, what was it, or 17 over 120. So if you plug in 1 half right there, this right here is going to be 17 over 120. That's what they're saying. So pretty much what they're saying is that the second partial sum is 17 over 120. Okay. Show that this approximation differs from g of 1 half by less than 1 over 200. So of course, if we're only taking these two terms right here, that's not going to be exactly what g of 1 half is, because g of 1 half is the infinite series. So by adding up all the terms, but of course we can't add that up, they're going to truncate the series here, and then they're using this 17 over 120 to approximate g of 1 half. That's what they're using to approximate it. Okay? Show that the approximation differs from g of 1 half so the difference between this and the actual value of g of 1 half, we want to show that that's going to be less than 1/20th. If you should be thinking alternating series error bound, which says that if you take the sum, subtract your nth partial sum, this error has to be less than the nth plus 1 term. So what they're saying is that since we're truncating it at the second partial sum right here, this entire error, this is going to be the error, the difference between my sum and my partial sum. Well, the most this error can be is the first omitted term. So this term right here is the most my error can be, and we're trying to show that it has to be less than 1 over this. So if we would put it into terms of what we're dealing with, you don't have to do this, but we're saying g of 1 half, which is the actual sum, minus 17 over 120 has to be less than the third term at 1 half. So I'm going to say, instead of saying that, we'll say, well, let's just use the term. X to the, what was it? X to the fifth. So we'll say 1 half to the fifth over 7. Well, what does that equal? Well, 1 over 2 to the fifth is 1 over 32, so I'm going to put that as 1 over 32 times by 7. And 32 times by 7 is 224. And that is less than 1 over 200. So, there you go. Our approximation, so this value right here differs from this value right here by no more than 1 over 224th, which happens to be less than 1 over 200. There you go. Okay, and for the last part of this question, write the first three non-zero terms and the general term of the Maclaurin series for g prime of x. So I'm going to do that up here for the sake of not having to go back and forth. So this series right here represents g of x. It wants us to find g prime of x. This really gets a lot of students confused, because they'll look at something like this and they're thinking, So I'm going to differentiate in terms of x. Any other variable in there, such as n, anything else in there, is going to be treated as a constant. Okay, so so you might think, well, I have to use the ratio test. I'm going to differentiate, right? I have a variable here, I got a variable here, so I'm going to do low d high minus high d low, square the bottom. No, because n is being treated as if it were a constant, as if it were a number, just like it's being treated here. So, for example, say n is equal to 0. Well, if n is equal to 0, then this right here just becomes 1, right? Yeah, anything to the 0 power is 1. So this becomes 1. So it's not a constant. So this right here is a constant. If n is always a constant, if n equals 0, if n equals 1, if n equals 2, this is always a constant. So it doesn't make sense to take the derivative here where I drop the n power, or I drop the n or something like that. Some people might think to do that. Or again, they might think that they need to use some sort of special rule here. No, we're only using the power rule, because n is a constant. We're treating it as if, like, if I were to plug in n equals 0 here, well, I get x to the first power over 3, which is what this term is. Well, how do I take the derivative of this? Well, I drop the power, decrease it to 0. Well, okay, well then this is just going to be 1/3. Okay? If I plug in n equals 1, if I plug in n equals 1, this becomes negative, which is why it's negative right here. Again, it's just a constant. If I plug in 1 right here, this whole thing becomes 3, and this becomes 5. How do I take the derivative of this? I drop the 3, I decrease the power by 1, divide by 5. If I plug in 2, well, this becomes positive 1, it's a constant. If I plug in 2 here, this becomes 5, this becomes 7. How do I take the derivative of a term like this? By using the power rule. I drop the 5, decrease the power, all over 7, so on and so forth. So for the general term, well, again, just treat this as if it were a constant, because it is. So for any term, what I'm doing, well, this one's going to be a constant, so that's going to stay as negative 1 to the n power, because eventually, if I plug in n, this is just going to become positive or negative. I'm going to drop the power, just like I did in all of these. If I drop the power, then it's going to become 2n plus 1 times by x. Now I'm going to decrease the power by 1, making it just 2n, all over 2n plus 3. So again, this right here is just going to be whatever power I'm dropping in the next term. And so there you go. You have the first 3 terms of the derivative, and you have the general term. Okay. So again, I'm kind of being repetitive now. I'm saying this a lot, but again, I'm just saying where students fail to understand a very important point. You're differentiating with respect to x. Everything else is a constant. You're treating this as if it were 5, as if it were 3, as if it were 7. You're treating this again as if it were 1, as if it were 3, as if it were 5. You're treating this as if it were plus 1 or minus 1. You're not treating this, any of these parts, like variables. The only variable is here. If I were to, say, differentiate this with respect to n, which I don't know why we would, but if I were to ask you to differentiate that with respect to n, yeah, you'd have to use all the special rules that we've ever learned about when differentiating. So I hope that makes sense. Okay, 7. Similar question. If f of x is given here, then find f prime of x. So just to kind of illustrate, if I build out the series, f of x, we're starting with n equals 1. I plug in 1, I get x squared over 1 factorial. I plug in 2, I'm going to get x to the 4th over 2 factorial. Plus, if I plug in 3, that's going to become x to the 6th over 3 factorial, so on and so forth. So f prime of x, well, okay, let's take the derivative. That would be 2x, right? Plus, if I drop the 4, that's going to become x to the 3rd over 2. That's going to become 2. Plus 6x to the 5th over 3 factorial. 3 factorial is 6, so those would cancel, right? plus dot 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 plus. If I go to the nth term, so again, n is going to be a constant, so those will remain as constants. So I'm just going to take the derivative of this as if this were just any constant. I'm going to drop that, so it's going to be 2n x raised to the 2n minus 1 all over n factorial. And there you go. There you have it. You have the derivative. This would be the derivative. I would say that f prime of x would be equal to series as n equals 1, 2n x to the 2n minus 1 over n factorial. Honestly, if you want to write it out kind of like this, I'm not going to say how many terms that need to be written, but if you are going to write it in like a polynomials type of way, at least write out two or three terms and the general term. Or if you want to go for it and write it like this with series notation, then that's fine with me too. Okay, the infinite series has nth partial sums. Here is its nth partial sum. So this is what the nth partial sum looks like. So s sub 1 would be equal to s sub 2 would be equal to, you can plug in 2, s sub 3 would be equal to, you can plug in 3, so on and so forth. What is the sum of the series of this series right here? So a very basic definition of the sum of a series is equal to the limit as n approaches infinity of the sequence of partial sums, so s sub n. So if you think about the s sub 1, the first partial sum, if I plug in 1, I'm going to get 1 for my first partial sum. If I plug in 2 for s sub 2, then I'm going to get negative 1. Plug in 3, s sub 3, I'm going to get 1. And if I plug in 4 for my fourth partial sum is going to be equal to negative 1. So the limit as n approaches infinity of this sequence, what's happening to this sequence? It's going from 1 to negative 1, from 1 to negative 1, and negative 1 to 1, and so on and so forth. So as n approaches infinity, it's either going to be 1 or negative 1, but it can't be both. Well, I guess technically it can be both, but that's the problem. It's both negative 1 and 1, which means that there is, we'll say this right here, in this case, so the limit as n approaches infinity of negative 1 to the n plus 1 does not exist. So therefore, the series diverges. So there you go. Very important that you guys understand this part right here. The sum of a series can be found by tracing the terms. Where are the terms of the partial sum sequence going? So the sequences of partial sums. If you can see where that's going, yeah, you can tell where the series is going. In this case, the series is going nowhere. Okay, what is the radius of convergence of the Maclaurin series for this right here? So I say don't use the ratio test. This isn't a series. Well, okay. This is the sum of the series. So the radius of convergence, the sum of this Maclaurin series is going to be equal to this right here. So this isn't saying that the series is this right here. That's not at all what it's saying. Basically what it's saying is that the series of, we'll say for a general term, a sub n, but this will also be a power series in this case right here, is going to be equal to 2x over 1 plus x squared. So that's what we're saying. Well, if that's what this series is becoming, this looks an awful lot like a sub 1 over 1 minus r, right? Well, yeah, this is then a geometric series. It's a power series and it's a geometric series, where the first term is 2x, and r, the common ratio, well, let's do just a little bit of algebra. 1 minus negative x squared is the same thing as what we have here, so therefore my ratio is negative x squared. Okay, and so if my ratio is equal to negative x squared. Remember, the absolute value of a ratio when it's less than 1, that's the interval, and this is the radius right here. So the absolute value of negative x squared has to be less than 1. X squared has to be less than 1. So what's my radius? My radius is 1. So radius is going to be equal to 1. There you go. Okay, for x is greater than 0, the power series, as stated here, converges to which of the following? So this is referring to the some common Maclaurin series. They're in 10.2. Yeah, I'll have these printed out for you for the test, but just keep in mind that for the AP exam, you're going to want to be familiar with them, or at least with 3 of them, I think. The 3 very common Maclaurin series that you're going to want to know are cosine of x, sine of x, and e to the x. Those are the 3 Maclaurin series that you're going to want to be familiar with. Okay? And they're really not that hard of series to remember, to be honest. And I'll state them here, and I promise I'm not even looking at a Maclaurin series. Promise. I'm not looking at them. I have no access to what they are. Okay, I'll just show you how I remember them. Cosine of x, well, cosine is an even function. Sine of x is an odd function. So, right? Yeah. Cosine of x is reflective, is symmetrical about the y-axis. Sine of x is not. So, considering that, I think about it like this. I use all terms. So I use all terms of the polynomial with degrees that are even. So the 0th degree, which I know is not even, but so 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial dot 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 dot. So this is the series for cosine of x. Again, it's going to be 2, 4, 6, less 2 less than that would be x to the 0 power, which is just a constant. Always cosine and sine of x are alternating, okay? And this is just always the same value as your exponent factorial. And sine of x is pretty much just going to be the values that are in between these. So the odd part, so that's going to be x to the first power over 1 factorial minus x to the 3rd over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, so on and so forth. And e to the x is just 1. It's not alternating, so it's 1 plus x, 1 over 0 factorial, x to the 1st over 1 factorial, x squared over 2 factorial plus x to the 3 over 3 factorial plus x to the 4th over 4 factorial, so on and so forth. So they're really not too hard to remember, and I would say that if you need to remember any, these are the 3 that you're going to want. Okay, so here's the power series here. Obviously, you can see here that this is not cosine. This is not sine either. I guess I can check for this one, but this one looks a lot easier to check before I check this one, right? So if I look at sine of x right here and compare it to here, what's going to be the difference? Well, this starts with 1, this starts with x, but if I divide this by x, I get 1. If I divide this term by x, divide all this by x, right? It's called a series expansion. So divide this by x, divide every term by x. What happens? You're going to decrease the power here, which makes this 2, which makes this 4, which makes this 6 over 7 factorial, so on and so forth. And there you go. So, has to be sine of x divided by x. Okay, I'm going to make another video for page 3.